Okay, looks like it's 9 and people are still joining, but that's okay. Today, we don't get started right away. So first thing we're gonna do is just help everyone set up. So today, as far as staff on hand, I'm here, Jeff is here, Will is here, Greg is here, Tina's here. I think that's all of our staff. Oh, Alex is here. Got a lot of staff on hand to help you out today. And a couple of things before we really get going. First, go ahead and log into the Rubin Science platform at data.lsst.cloud. It's the browser you use, the URL to use in any browser. And today we'll be doing sort of notebook and portal sort of at the same time. The tutorial is going to switch a little bit between them. It's all about tap queries, which you can do both in the notebook and in the portal. So go ahead and open up two browsers or two browser tabs, one with the notebook open. And once you have your notebook aspect open, open the second tutorial. It's called Intermediate Tap Query.ipynb. And then in the other browser tab, just open up the portal. So you have those two things ready. And as you open up those and get started, you run into any troubles, you can unmute and ask questions, or you can post in the chat. All the staff on hand are also monitoring the chat so we can help you in real time. After we have this, first we're going to do like a few announcements, then we'll do about an hour-long tutorial, and then after that we'll have lots of time for breakout sessions. So some of today's breakout sessions are over here listed in the right table. The main room will stay open, of course, just for general questions. And then we're gonna have a little science collaboration new friends program, little meet and greet in one of the breakout rooms. I'm gonna lead that. I'll tell you more about that program in a second. Jeff Carlin is going to lead a tutorial on how to make single star light curves with a new notebook in another room. And then I have in italics a couple of suggestions, some of the breakouts we had last time on large scale structure. Maybe the people who were there want to repeat that and tag up again about that work. Maybe some people want to meet up and do advanced portal queries. That's another option. So if you have suggestions for breakout rooms or topics that you wanted to work on today, and you're looking for a couple of other like-minded DP0 delegates to join you and you want to suggest a breakout room topic, get try unmuting at any time or put it in the chat and I'll put it on this list. And then once our tutorial hour is done, we'll come back to this list. I'll make the breakout rooms and then away we'll go. I'm just gonna pause for a second before moving on to announcements. Okay, the two announcements that we have today. One is an announcement from the science collaborations. Everyone is welcome to join a science collaboration if you haven't already. It's a great way to learn about Rubin and to find people to work with. Science collaborations support research and especially preparatory work for LSST. And these are the 8 science collaborations there. They've also started what we're calling the DP0 New Friends program, in which they set up partnership pairings between their members who've been science collaboration members for a really long time, and they're looking to pair with people who are coming to DP0 who are either new to Rubin or coming back after a long break and sort of are just looking to make new contacts and have someone help them a bit with all the nuances and all the details about working in a science collaboration. So if you're interested in that program, either as a new person or as an old hand who's been in the science collaborations for a long time, if you go to the URL ls.st/CLO5700, it explains what this program is a little more and where to, it's a Google form to just sort of drop your information in and we'll pair you up with someone. So far we've paired up, I think, 7 pairs, about 14 people, and we have a couple more pairings that we're looking to make as well. So please do consider it. And if you're interested at all, or if you're already a new friend or an old hand partner, drop into the breakout session that we're going to have after the tutorial. The second slide that I wanted to present, and I think Jeff will go over this again when he starts the light curves tutorial in the breakout session later. We know a lot of people want to do time domain science with DP0, but we do need to set some expectations for what you can do. So first, DP0.1, it doesn't provide an accurate preview of time domain science with LSST. DP0.1 is a very, very early preview of what's to come, and multi-epoch force photometry was not run in DP0.1. So there's only so much you can really do at this stage. And this 9th notebook that we've added to the tutorial notebooks repository is really just a temporary workaround that's only meant to be used for a very small number of objects, so like 1 to 10s, not hundreds, not even the like thousands or millions that you'll actually be using with LSST. So it's very, very, it's very slow. It's a workaround. It does not represent how light curves will be built and accessed in the later data previews, and definitely not in operations. So it's not like it's not even a good learning tool. The point of DP0 is for you to learn how things will be in operations. And this notebook it's a total workaround that's not going to teach you that, but it will get you a couple of light curves to work with now. Really, it was designed to demonstrate the limitations of trying to do time domain science with DP0.1. And the official recommendation is that delegates who are interested in time domain astronomy just wait for DP0.2, or at least limit themselves to just starting to investigate just a few objects. DP0.2 will be quite different for time domain astronomy. It'll contain forced source table that will have the light curves obtained by forcing PSF photometry at the position of all objects, where objects are everything that's detected in either a single visit image or a deep stack, or difference images. So DP0.2 will also have difference imaging, which of course is what time domain scientists really want. So I hope that kind of helps to set expectations of what you can do now and what you'll be able to do later. But with that said, if you're interested, please still go to Jeff's breakout session later and he'll show you what can be done. He's developed like a good notebook for you guys to use. So with that, we'll just pause for another like minute or two, see if anyone's had problems logging into the portal or the notebook aspect. And then we'll start with the tutorial in like 1 minute or 2 minutes. I see nothing in the chat yet, so maybe everything's just going well this morning.
Is the new notebooks are available, or should we are they installed already?
Yes.
So we should from our side, should we update the notebooks?
You shouldn't have to. So when you're in the notebook aspect and you're in your notebooks, tutorial notebooks directory, this updates automatically whenever we update the tutorial notebooks. So you should have what you need already.
I just open and I don't see the exercise number 9 in the list. So should I make update for the notebooks myself?
Yeah.
I found this morning that that if you log out and then log back in, then it'll pull the updated notebooks. Because I think it might be that if you hadn't logged out, then it doesn't re-pull that repository.
Thank you. I will try that.
Yeah.
Sure.
Yeah, we added number 9 yesterday. So if you've been logged into the notebook aspect since yesterday, yeah, you probably won't see it. But yeah. But it's number 2 that we're doing for this first tutorial. So open number 2 first. Okay, go ahead and feel free to ask more questions. I'm going to stop sharing my screen. Leanne Guy is the one who's developed today's tutorial, and she's going to be the one leading you through intermediate tap queries today, while the rest of us answer questions in the chat as she goes. So take it away, Leanne. You ready?
Yes, I am. Can everyone hear me, and can everyone see my shared screen?
Yes.
Yes.
Yes, thanks.
Okay, so let me just organize my screens a bit. Okay, so in my browser, I have two tabs open. I have here the Science Platform portal. As Melissa mentioned, we're going to flip a little bit between two of them today. We're mostly going to focus on notebooks, but I'm going to show you how to do the same thing in the portal. Then next to it, I have the Jupyter Notebook tab. So this is the way I find to work. I'm going to run through everything here. Please feel free to follow along at home. I'll go at a pace that I hope you can follow at. If you have any questions about cells or as we're executing, please stop. I'll ask one of our other moderators from the team to moderate. If hands go up, to stop me, and we can go back and forth and answer questions. Okay, so we're going to start in the notebook. And as has already been mentioned, we're working on Notebook 02. It's called Intermediate Tap Queries for DP0 catalogs. I'll just walk through this. The learning objectives for this tutorial are to introduce the delegates to how to use, how to execute queries on the DP0.1 catalogs from a notebook. And we do this by building queries in something called ADQL. It's the Astronomical Data Query Language. It is very similar to SQL, Structured Query Language. In fact, it's built on SQL, but has a lot of extra functionality for astronomy and for astronomical data queries. That's how we build our queries. How we execute our queries, how we send them to the science platform is over something called TAP. This is Table Access Protocol. It's an IVOA protocol that has been implemented in the Rubin Science platform and will allow us to send queries to the science platform, to the database, and to execute ADQL. So we're going to look today at, first of all, we're going to explore the DP0.1 schema and catalog using the TAP service. We're going to then look at how to query the object and the truth match catalogs to retrieve some data. We're then going to plot that data and do a very small amount of analysis. I won't focus too much on the plotting. We'll do a little bit of visualization, and then I will show you how to execute asynchronous tap queries and why asynchronous tap queries are useful. So the first cell is called setup. Execute the setup cell. Actually, let me just refresh. It's always good at the start to go to kernel and hit restart kernel and clear all outputs. And I'm just going to do that again because clearly, given that it's come up with number 35, I've obviously been doing something. So go to the setup cell, execute your setup cell, and that should run. I won't go through the details of this because Melissa covered it in the previous one. Basically, you're just doing all the imports from, we have some general Python packages, we have some AstroPy packages, we're using Bokeh for interactive visualization. We set a few parameters for pandas for the maximum size of the table that gets printed. You should see a note here that says Bokeh 2.3.2 successfully loaded. The next cell is just something that I like to do to ignore a lot of the warnings. So a lot of warnings come up and sometimes I find they get in the way, so I like to just ignore those. You can turn that off. I will not execute it as you like. So the first thing we're going to do in section 1 is to explore the DP0.1 schema. The TAP protocol provides us access to catalog data for discovery, search, and retrieval. There is a link here to the full TAP documentation, and it is provided by the IVOA, the International Virtual Observatory Alliance. As I said, it's similar to SQL, and there's a link here for detailed documentation on ADQL. We will not cover everything that's part of the ADQL standard today, and I'll also point out that not all ADQL functionality is implemented yet for DP0, for the Rubin Science platform as part of DP0. So as Melissa's explained I think several times, this is a work in progress. If you try to execute something in ADQL and it doesn't work, ask on the forum, but just bear in mind that not everything's available yet. So in the first cell here, and I'll execute it, we create an instance of the TAP service. And Rubin, the Rubin Science platform provides some utilities to help you do this. If you import from the Rubin Jupyter Lab notebook tools, we have two methods called get tap service and retrieve query. And so we call get tap service. The second line here is get tap service, and this returns us an instance of the tap service, and that's the tap service we're going to work with to execute queries. Just to ensure that we have got a valid tap service returned to us, I always like to run assertions as part of my cells. So I assert that the service returned is not none, so we don't have a null object. And I also assert that the base URL as part of the service is the correct one for the Rubin Science platform. And you see this is here, data.lsst.cloud/API/tap. So an assertion is basically just an expression which, it's a Boolean expression which will evaluate to true at a point in the program, provided there are no bugs or errors in your program. And I find this very useful because if these assertions evaluate to false, the program will stop and it will alert me. So I catch errors early. So does anyone have any problems with setting up their TAP service? Jeff, you can give me that okay to go on or not. Jeff or Melissa? I think I'm not seeing any hands up, but I can't see everyone. Okay, so we all have a TAP service. Excellent. The first thing we're going to do now is use our TAP service to discover what schemas there are available as part of DP0.1. So in this line here, I first define a query, and this is just a string in Python. It's very simple. Select star from tap schema.schemas. Okay, select star means select all the columns. From tells me the schema and the table to select from, and it's called tap schema.schemas. If you go over to the portal and you select on edit ADQL, so you take number 2, select query type, edit ADQL, you'll see to the left here that there is a schema browser. If you click on tap schema, you will see tap schema.schemas, and it is exactly the same as what we're calling here in the notebook. So if I go to the portal and I open this, I will see all the columns that are available as part of this table. To execute this query from the notebook, I then pass the query to the search method of my TAP service, and it will return me a result set commensurate with that query. So I'll execute that cell. It executed very rapidly, which is good because it was a very simple query. And if you take a look at the result set that's returned, I just print here the type, you'll see that it is a virtual observatory TAP result object. And Python, there is a PyVO package which defines this TAP result object. To make it easy for us to work with the result set in a way that many of us are familiar with, we can convert this to an AstroPy table and then display the results. So I'll execute the next cell, and you'll see here it will print up the table that has been returned. And this table has the columns description, schema index, schema name, and UType. If you go back to the portal, you will see these are exactly the same columns as you see in the browser. Schema name, UType, description, and schema index. I'll just pause there and wait for Melissa and Jeff to give me the okay that everyone's.
Do you mind just me asking a question, like without? So it says UWS metadata. So if I don't know what that is there an easy way to find out what this tells me?
Sorry, which one are you looking at?
I hit the next one, where you say it prints it out, convert the results to an AstroPy table and display.
Yes. UWS metadata. Yes. This is, we don't see that in TAP. I think this is something to do with QServe. I don't know if Will knows or if Colin or Fritz are on.
I can't actually see your screen, but I'll have a look and I'll see if I can figure it out in the background. I'll run your notebook.
Thanks. Yeah, because UWS metadata, Catherine is right. It comes up in my TAP query, but I don't see it in the TAP schema. All right, thanks, Will. But the one we're interested in is the DP0.1 catalogs. Okay, so we have a schema. All of our catalogs for DP0.1 are part of the schema name DP01_DC2_ catalogs. And these are the only catalogs that are available at the interim data facility. And it gives here a description that tells us it includes 5 tables based on DESC's data challenge 2, simulation of 300 square degrees of the LSST wide fast deep survey to 5-year depth. All tables contain objects detected in COAD images. So in the next cell, this just shows you a small piece of code that allows me to extract the schema name into a variable. So you could just copy and paste that if you want into your future queries, but I just do a little bit of Python here to extract the column schema name from the result set. And then I loop through that to search for anything matching DP0.1. I break when I find it, and I store that as a variable. DP0.1 schema name is equal to DP01_DC2_ catalogs. And you'll see it now prints out the DP0.1 schema is DP01 DC2 catalogs. So now that we have our schema for DP0.1, we can now explore the tables that are in them. And if you execute the next cell, here I prepare a query. I'm going to do a select all columns from the tap schema tables, which is the same as my first query, but now I'm going to specify that where the tap schema tables is equal to the DP0.1 schema name, and then I'm going to order my results by the table index. So this is the query. I just print out the query here. Often I print out the query. You can cut and paste this, and if you want, you can go to the portal. You can plug it into the ADQL, and then you can search there. It's a good way of checking the syntax of your queries. If you're building a query in the notebook, you cut and paste them into the browser, and here you see the result set has been returned. So now in my next cell, I will execute this query. I will then convert it to an AstroPy table and print the results. And you'll see here that we have the 5 catalogs that are part of the DP0.1 schema, and they have been ordered according to their table index. The table index is internal to the database, and it's used to determine how the tables are presented, the order that the tables are presented in by default in the portal. So we have here the object table, the truth match table, the position table, the reference catalog reference table, and the force photometry table. So I'll just pause there for a minute and see if there are any questions on this or any comments. No, I could move on.
Yeah, I think so. Yeah.
Okay, so some of you may be very familiar with SDQL, and yeah, and thank you, Leanne, for the thumbs up. Please feel free to give me the thumbs up if you're happy for me to continue. So I've added here some definitions for people who are unfamiliar with TAP or ADQL or who haven't got much experience working with databases. A schema is basically just database terminology for the abstract design that represents the storage of data in databases. A TAP schema is the specific schema describing the TAP service. All TAP services have to support a set of tables in a schema called TAP schema, and they describe the tables and columns that are included as part of the service. So if you're executing something of a TAP, you know you will always find a schema called TAP service. A table is a collection of related data held in a table format in a database. So this is, for example, the object table or the position table. These are often referred to as catalogs as well. This is the data that you will mostly work with. A collection of tables is DP0.1.DC2 catalogs. So these are often grouped together to form some sort of logical set of tables. So for example, we might also have one day the Gaia tables in here. So you could group those into a schema for Gaia with all the Gaia tables. You might have data from other surveys as well. And the results are the query. So when you execute a query over TAP, you get back a set of results, and these are stored as a TAP result object. And you can then convert that to a variety of different formats as you like. Okay, so now that we understand the schema a little bit, we know how to navigate around, let's take a look at the object and the truth match catalog, because these contain the data from DC2 that we're interested in playing around with. If you want to find out more about the object catalog and the truth match catalog, take a look here at Desk's DC2 data release note, and you can find more in Desk's DC2 paper. We have a lot of details in here. We won't cover everything today. I'll just introduce you before we start to execute larger queries into a useful utility. You can set a limit on the number of rows that you return from an ADQL query. And this is very useful when you're building your queries and you're testing them so that you don't get back billion row objects all the time, because that will be very inefficient. And if everyone does this all the time, it might not be very good for QServe. So if I execute the first cell in 2.1, specifying the maximum number of records to return, you see I define a parameter called maxRec of 5. And in my query now, instead of doing select star or select a set of column names, the first thing I do is say select top, and then I pass in my maximum records parameter, and then I list all the columns that I want to get back, then I list the table, and then I list my criteria. So you see if I print this query out, it's select top 5, which means the first 5 rows that are returned, as well as the object ID, the right ascension and declination, a few more parameters here from the object catalog and I'm going to put some some filter criteria here. I'm going to select those objects for which the extendedness is 0 and the R magnitude is less than 24. And then I'm going to order them by R magnitude. So if I execute that query, I have an assertion here which says that the length of my result set should be equal to the maximum records, and you can see that my assertion was true because it didn't throw an error. Therefore, I have 5 records back. You can also print out the results of that query if you like. You can also copy and paste that query, put it into the portal, into ADQL. If I copy and paste it and put it here like this, and I execute a search, and you can see I have 5 records back. They are, and they all have extendedness 0. So that was the criteria that I applied. And I ordered them by, what did I order them by? Again, descending R magnitude. And you can see that the R magnitude here is indeed descending. So it's very useful, especially when you're building and testing your queries. You want to make sure you're getting things right. Don't do your testing and attempt to get 1 billion rows back. It'll be very inefficient. There's another way of doing this as well. If you look in this next cell, you don't have to put top X into your query. You can use the maximum records parameter with the search method on the tap service. So you keep your query as is. You then pass it to service.search, but you specify maximum records equals the value you've set. And if you execute this, and again, I have the same assertion, which is passed, so I also get 5 records back. The way you do this in the portal is to set the row limit down here to be 5. Let me remove now top 5 from my query here. So now I'm just doing select my parameters, same table, same filter criteria. I'm setting the row limit down here to be 5. I go on search, and it should also return me just 5 records. These 2 ways of limiting the number of rows that you get back from a query are identical, okay? There's nothing different about them. Use whichever one you like, whichever is easiest for you. Okay. Now just to show you again, here's another assertion in this final cell. I have 2 result sets now obtained by 2 slightly different methods, and I use Pandas has, is it Pandas or Python? It's Pandas. Has a nice assertion utility function called assert frame equal, and here I assert that the table that I got from using maximum records and the table that I got back from using top 5 are identical, and my assertion passes, therefore they're identical. Any questions to this point?
There is a question. I assume that select top 5 gets executed before the order by neg R desc is that correct?
I don't think so. SQL should do the query and give you the top 5 from that query. So the order should be preserved, especially if there's an index for it. But that's like a deep SQL, nothing to do with QServe. And from my ancient teaching SQL to people.
Yeah, I think Will's right, but we should maybe make a note, Melissa, just to check that with Colin and Fritz, that that's exactly how it works.
Okay. Another question. Where can I see maybe how many points there are? I put 100 and got no coverage area. We might need a little more details about what you were trying to do. It's coming from the chat.
So do you mean top 100 like this?
Oh yeah, instead of top 5, top 100.
Okay.
But no coverage area usually means you've tried to search, like some other search parameters are out of bounds.
Yeah, so let me just execute this. Do you mean that you're saying top 100, but you're not getting 100 results back? That probably means that there aren't enough results that satisfy my other criteria, and it's returning them the maximum up to 100.
Oh,
This does show me that I get 100 results back. So I'm not sure if that's the question.
might have been a typo. I think we have a report that maybe the problem was something else. And then one more question while we're paused is that we got some reports that the notebook was returning spawn failures and just returning blank screens, and some people weren't able to log in. And if that's also occurring to you, please do pop it in the chat. It helps us to know how many people are experiencing this and where you are. Try and fix whatever it is.
Just a short note, that was very slow for me, but I just connected.
Okay, we tried to avoid this issue. I guess it didn't work. So please do pop in the chat if you are having troubles. We want to know if you're having troubles. And then Leanne, as we get started again, there's one question. Can you show again how you do the result one ADSL query?
The
So you
result
should-
one. Do you mean this one here? Can you see my screen where I've highlighted it? Is that what you mean?
Actually, I'm not sure what's meant.
Oh no, I mean in the tab, in the portal there.
Ah, okay.
I don't think I see the query just now.
Ah, okay. So let me go back here. I didn't copy and paste it this time. I just edited it because it was a very simple change.
Ah, I see. Okay.
So the only difference between the two queries is that the first one
It's with top 100, let's say top 5 on the very beginning of the sentence. How about the second types?
if I leave row limit here empty and I do search,
Oh. So you just do the row limit, just change the row limit into 5. Oh, I see. I didn't see that you changed that just now. Okay, thank you.
so when I remove top 5, I then set row limit. Row limit in the portal is equivalent to setting the maximum records parameter in the service.search API.
Yeah, I got it now. Okay, thank you.
Okay, any more questions?
You're good to keep going. Thanks, Leanne.
Okay. Excellent, we're halfway through. Okay, so now let's do something more exciting. Let's do a cone search around a point with a specified radius. This is something very common that we like to do in astronomy, and it's also somewhere where you'll see now some of the added functionality of ADQL. So we're going to execute a cone search on the object table centered around a position. For this, we're using 62 in right ascension and -37 in declination. Just why not? There's nothing special about that position. And we're going to use a radius of 0.1 degrees. We're going to apply a cut on magnitude, and we expect to get a result set we expect to get 15,670 results. So we're going to use this position and radius throughout the rest of the examples. So to simplify our life, we're going to define them as parameters so we don't have to type 62 and -37 and 0.1 all the time. And I like to use the AstroPy sky coordinate object. Here I can define a coordinate on the sky with a right ascension of 62 and make use of the AstroPy units. So I set degrees. Likewise, I set a declination of -37, specifying that this is a unit in degrees, and I specify my frame of reference. I then have a radius of 0.1, and again, using the AstroPy coordinate degree, I specify the unit. We're going to use these throughout the rest of the examples, and when you set these numbers, define them to a variable, then if you consistently use the variable, you ensure that you do the right thing all the time. And you don't make a mistake by typing 61 instead of 62, or leave off the negative sign, which is very common. So as before I prepare my query, this time I'm going to select the right ascension and declination. I'm going to select the magnitudes, I, G, and R magnitudes. I'm going to select the C model magnitudes. I'm going to select the PSF flux. I'm going to select the C model flux. I'm going to select the patch, the tract, the extendedness, and good and clean are two quality flags that have been defined on all of the objects. I will select these from the desk object catalog. I won't spend time to, we've only got another half hour. I won't go into the details of what the difference between the C model magnitude is, the other magnitudes, the PSF flux, the C model flux. Please refer to the desk paper to understand how these were computed. There's a lot of detail in there. I do my selection on the object catalog, and here is where we do the cone search. Here's where I define my cone search. I say where my query is based about a point in the ICRS reference frame, right ascension and declination, and then I define a circle. Here I pass my coordinate RA value, my coordinate declination value, and my radius, my search radius. So let me execute that. Oops, sorry, let me execute that cell first. Then let me execute that cell. And you can see that this prints out the query. You can copy and paste this query and put it into the portal to run this as well. Let's just go back to the notebook. So you're specifying a point defined by a right ascension and a declination in a coordinate frame. and you want this to be a circle, you specify here the exact right ascension and declination and the radius. As before, we take this query, we pass it to the service.search method. Now I'm going to do it in one step. I'm going to convert this to a table, to an AstroPy table. And then from the AstroPy table, I can execute another method which converts this to a pandas table. So many of you will be very familiar with working pandas. You can do this all in one query if you like. You can just add these two methods, to table, to AstroPy table, and to pandas in one. I will execute this cell now. Again, I'm using an assertion on the length of the result set to make sure that I get the right size result set. This is executed and my assertion was passed. I'm going to run this again and just point out that you see that the cell continues to run. This was actually very fast, so that's good. But you'll see that the cell continues to run until the search method has completed. This is a synchronous query. So I execute the query, the cell continues to run, it does not return until the query is finished and the assertion has been executed. We'll see later in about 15 minutes how we can do an asynchronous query where this doesn't happen. Okay, and in the portal, you'll see that I also have 15,670 results, and you can see these are all the columns that I've queried, and you can compare the results that you get with the notebook. So now that I've done my cone search, that's all very nice. But one of the things we typically want to do is to compare the results in the object table that are a result of processing. So the Desk Science Collaboration ran the LSST Science pipelines on their simulated images, and they produced the results that you find in the object table. We want to compare this often with the truth information. So now we get to a slightly more advanced query where we are going to join two tables in the DC2 schema. We take the object table, as you've already seen, we have the truth match table, and we join them by matching on the object ID. And then we can get the true magnitude or the true fluxes, and we can then compare those to the recovered fluxes from running the science pipelines on the simulated images. And that is this query here. It is a slightly more complex query. Maybe I'll just stop and just check if there aren't any questions from the previous query.
There is one question. It's just about pandas and whether there are any specific benefits from working with pandas. If you're already comfortable with AstroPy tables, is it?
Do what you're comfortable with. Pandas is very powerful. I mean, I'm not going to go into the details here because it's outside of the scope of this tutorial, but I would encourage you to have a look at pandas. It's very powerful for doing data manipulation. But if you're happy with working with AstroPy tables, stick with AstroPy tables. They also contain a lot of good functionality. The previous queries we left as AstroPy tables. I'm just trying to show a variety of ways of working here. Okay, so let's now take a look at this query. I'll execute it to build the query. And I didn't print the query here, so let me add a query. Okay. So I'm going to select now some columns from the object table, and I'm going to select some columns from the truth match table, and then I'm going to match them on their common ID. And to show you how this is done, I'm just going to go to these middle lines first. And this is the from statement. So all these first columns here are the columns that we want to select from both tables. We say we select first from the object table, and then we assign the object table a short name OBJ for ease of typing. We don't want to always type DP0.1 underscore DC2 underscore catalogs. That's a very long name. So we assign the table name here to a short variable called object. And if you look in our select back here, the columns that we want to specifically select from the object table are prefixed with OBJ. So we have obj.objectID, which means it's the object ID stored in the catalog's object table, which has been assigned to this variable OBJ. Likewise for the right ascension, the declination, the G magnitude, the R magnitude, the G model, the C model G magnitude, the C model R magnitude, etc., etc., etc. Also the extendedness, the goodness of fit, and the clean parameter. These are all part of the object table, so we prefix them with OBJ. Note that tables are separate entities, and so you may have columns into tables which have the same name. And when you do a join, if you don't specify exactly which table the column comes from, you can have clashes and your query will fail. So this is very good practice when you're doing a join to make sure you assign the table that you're querying to a short variable name. So we say first from the object catalog, and then we join. We use this SQL statement join, and we join the object table with the DC2 catalog's truth match table. And we assign the truth match table to a name of truth. So come back now to the top. The columns that we want from the truth match table are truth.magr. And you'll see that object table also has a magr. So if we hadn't specified object.magr and truth.magr, we'd have a clash and the query wouldn't know where to go and it would fail. So now from the truth table, we select truth.magr, and we can also assign these to different variable names here, truth.magr as truth_mag_r. You don't have to do this, but you can do this to make sure that the column names in your join table are easy to understand. So I choose the truth match object ID, I choose the truth match flux in G, a few others as well. An important parameter to choose is the truth match truth type. So I know, was it a star, was it a galaxy, was it a supernova? Because in the simulations, the desk knew what they were simulating, so they assigned the type of object. The separation, the match separation is variable. There are a whole lot of other parameters as well. I've just selected some, but feel free to go and consult the catalogs and play around with this. So we're joining on the truth match table, but we have to say how we're going to join. How do we know which row in the truth match table corresponds to another row in the object table? This is where the on parameter comes from. On tells us which two columns, which column in one table and which column in another table to match up. And so we say on truth match object ID equals the object ID. So in the truth table, the column is called match_object ID. In the object table, the column is called object ID. These are the same object IDs in different tables. In this case, they have different names. So we specify the table name and the column name, and we match them on that column. Then, as before, we include our cone search because we want to look in the same cone that we defined before, using, again, substituting the coordinate values from our asterisk by sky coordinates object and the radius. And here we have some different quality criteria. We want to make sure that the object ID in the truth match table is greater than or equal to 0. If you look in the desk documentation, you'll see that if there's a match object ID less than 0, this indicates, I forget what it indicates, but it indicates something's wrong. I forget, maybe Jeff or Melissa remember, but you don't want to match on negative object IDs.
Right, the way the matching is done is it looks for a match for every object in the truth table. So if it didn't find a match in the measured catalogs, then it sets it to -1. So if you say greater than or equal to 0, you're only picking the ones that had a match.
Yeah. And then you also want it to be a good match. You set that equal to 1. 1 is true, 0 is false. So this is something you also have to watch out for with SQL. So we want the match to be good as defined by the desk quality criteria. And you can find more details about what exactly makes a good match in the desk note. So now, as before, we pass this query defined above to our search method as part of the TAP service. And I am converting my result set to an AstroPy table and a pandas table. And my assertion should tell me that I get 14,424. This has returned already. My assertion has passed, so this is good. And just to do a bit of subsetting to have a look at what I've got. This is where pandas, this is using the pandas data table to do subsetting. I am now on the truth type. I pull out the number of stars. I match here on 2. 2 is the truth type for stars. 1 is the truth type for galaxies. 2 is the truth type for stars. 3 is the truth type for supernova. And I'm just printing some statements here where I subset the result set by truth type on 1 or 3 or 2. And I see that most of my results are in fact galaxies. Over 14,000 of the results set are galaxies and a very small number of stars. So I'll just pause there at the end of that to ask if there are any questions. That was quite a complex query. Does that query make sense to everyone? I'll also copy and paste this query and then go into the tab, so into the portal.
I haven't been following super closely, but does it make sense that there are no supernovae returned?
Yeah.
How did you exclude them?
I didn't exclude them. It just
Alright.
happens that the point on the sky that I've chosen doesn't have any supernovae.
Oh, it's a small.
Exactly. I've
Ah.
chosen a small point on the sky about a cone. I think what I might do is go back and update this notebook to choose a point on the sky where there are some supernovae, just to demonstrate that all three types come up. So yeah, it's not a bug. I've executed this search on other parts of the sky, and there are supernovae.
I see. Okay. Another question about pandas, about why doing .to-table .to pandas. But I think that's just if you like to use pandas, that's how you use it. Yeah.
And I haven't used AstroPy as much. Pandas is very powerful for subsetting and manipulating your data and looking at it different views. But, again, it's up to you. If you want to use AstroPy, use AstroPy.
Mm-hmm. And I see, Sahar, you've got your hand up, but you're muted.
Muted.
Sahar, did you want to ask your question? You're muted.
You're still muted.
Sorry.
Oh, there we go.
Why adding both? I think one of them is enough.
Adding both what? Sorry.
Dot table and dot panda.
Dot to pandas. So if you want to work with an AstroPy table, you can just do that. My assertion might not work. Yeah, okay.
Maybe the question is, can you do just to pandas?
No, I do not think that you can. Fairly sure, maybe you can. No, you can't. The tap results object does not have a method to convert directly to pandas, but it does have a method to convert to AstroPy, and AstroPy does have a method to convert to pandas.
So the result from TAP is AstroPy, to be clear. So you're converting to Panda from AstroPy. It's not the same for everything inside Butler. Some other things are actually coming back more closely to Panda, especially if there's Parquet underneath. But in this case, you're doing an extra step for Panda. If you just chose AstroPy, that's what's coming back anyway.
Okay, there's one more question in the chat that I'm not sure I understand. Which SQL database is used? Is it MySQL?
No, the database, the LSST database is QServe. It's an in-house development to store and to be able to manipulate the very large data set that LSST will eventually handle.
Okay, and one more question. Are the conversions fast if we have more objects?
Conversions, you mean between table types?
I'm guessing yes. Yes.
I've never found it to be slow. This is a 15,000 row data set. That's not particularly big, but it's not 10 either.
Yeah, so maybe it might get slow. There's many.
Not in this example, but in completely other contexts, I have run these conversions on different size tables. I've never found it to be a problem.
Okay.
I would encourage you to, you can simulate a data set, create a 1,000,000 row table and try it out yourself if you like.
Okay, no other questions, no other hands. And I'll just note about 10 more minutes, probably zoom through the visualizations. Yeah.
So we have 10 minutes left. In the interest of time, I'm going to skip over the visualization and analysis of results section because the focus of this tutorial is on ADQL queries in the TAP service, and I don't have time to go through everything else in the notebook. But please feel free to go through this and have a look at how to use bokeh and holo views to visualize these data sets that have been returned. Using bokeh and holo views is an entire tutorial in itself. I'm working on an advanced visualization notebook, and perhaps in the future we can do another run through of how to do some advanced interactive visualization with these data sets. But for now, I will leave the visualization of the results that we've just retrieved through these ADQL queries as an exercise for you all to run through. Please feel free to ask questions on the community platform. I'd be very happy to answer them, and so would everyone else in the community engagement team. This gives examples of how to prepare your data for visualization, how to do a color magnitude diagram, how to do a color diagram, and how to do brushing and linking between diagrams, and then how to present a comparison with the truth information. Okay, let's skip through to section 4, asynchronous tap queries. So when your query is very large, it can take a long time. And what you don't necessarily want is to have your cell stalled while you wait for a query result to come back. Your query may end up taking 5, 10, 15 minutes. You might want to go away and have a coffee. You might want to just let it run. So in order to do that, you can run asynchronous cat queries. Another advantage of this that we'll look at is that if you've run a query in the past and the results are still stored on the server, you can get the URL and go back and retrieve a result set for a query that was run maybe half an hour ago. So you can work completely asynchronously. So let's have a look at how to do that. We're going to use this query. This is the last query that you executed, and this is the query that does the object catalog and truth match catalog cross match. So we submit a job now, rather than do what we did before. The method we used before was search. We did service.search and we passed the query for a synchronous query. Now, what we do is we submit a job to the tap service. That should execute very rapidly, this cell. We submit the same query, we submit as a job, and then from the job, we can get the job URL. And this tells me the URL now to my job. And then we can get the phase of the job, which says it's pending. So we have prepared a job, but we have not yet executed the query. Now we run the job. And you will see that the cell returns immediately because the execution of job.run is instant, and it tells the job on the server that it should run. This doesn't mean, however, that the job is complete. In the next cell, we execute job.wait. We define job.wait in our phases completed an error, and then we print the job phase. In this case, it's completed. For a longer, slower job, and in fact, if all of you try to execute this now at the same time, you'll probably find that when you execute this cell here, your job might not yet be completed. So try to do oops. Sorry, I need to execute everything again. And now my job's completed. This is a very useful function here called job raise if error. If there is an exception thrown or if there's a problem with the query, you can find out what that was. So now what's happened is we've defined our asynchronous job, we've submitted our asynchronous job, we now want to get the results. So then we go job.fetch results. And this will bring our results back, and I will store it in an object, a variable called async results. Now, as this is the exact same query that we executed via a synchronous search, we expect the exact same result size. So I've run an assertion now to assert that the length of my asynchronous query result set is the same as before. And I've also executed the frame.equals to show that my results and my asynchronous results are identical. And they are, so that's good. So I've got exactly the same results back by doing an asynchronous query as I have for doing a synchronous query. Again, these are very useful if you have long, detailed, complicated jobs. So does anyone have any questions on that before I move on to the next and penultimate cell? I don't see any. Jeff, Melissa, do you have any questions?
No, it looks like you're good to continue.
Okay, so job results may still be available on the server from queries that were run half an hour ago, maybe even a day ago. It depends on how enthusiastic the cleanup mechanisms are. So if we have the URL for a job, we can retrieve the results. We do this by running retrieve query. This is one of the utility methods that's provided by the Rubin Science Platform notebook utilities that if you remember, we imported in the very first step as part of our setup. So you can execute retrieve query and you pass it the job URL. The job URL is the URL that was defined and assigned to our job when we created the job at the beginning, and that we printed out here, and that is stored in job.url. So you pass the job.url to retrieve query, and you get your retrieve job, and then you do retrieve job fetch results, which is in fact similar to, which is the same as job.fetch results. And then I do an assertion to check that I've got the same result set back, that it's got the same length, and I do a frame assertion to check that it's identical, my assertions pass, and so all is good. So I have retrieved the result set by passing a URL from a previously executed job. Now, one way in which this can be useful is if you go now to the portal, here is the result of the query that I executed before with the join in the portal. If you click on the parameters here, the cogwheels, it'll bring up a box called table options. And if you'll see you have 3 tabs here. If you go to table metadata, you will find the URL to this job. You can copy that, go back to the tap service. Now I'm going to substitute that and put that URL in there instead. And it will now retrieve the results from the query that was executed in the portal. In this case, it's in fact the identical query to what I ran through the notebook, so my assertions also pass because it's the same query. Let's really demonstrate that works by going back and executing a different query that will give us a different set of results. Let me just pull up one. Let's just execute this one here where we don't do a join, because we get a different size result set. So this now is just my simple query on the object table. So it's running in the portal. Here I get 15,670 results back just from a simple query in the object table. I go to the cogs, I click on the table meta filter tab. I copy the URL. I go to the Jupyter Notebook. Go back down here. I pass it this URL instead of previous one. You'll see that's a different URL. Now I run retrieve results. Right, now you see it throws me an error and it points here to my assertion. My assertion has failed, which I expected to fail because I've got a different set of results that's returned. So let's just comment that out for now and do print length retrieve results. And you'll see it's 15,670, which is the same as what we saw in the portal, which is the same as we saw with our previous query. So I'll just pause there and see if there are any questions on that and ask if people understand that, if it makes sense.
I had a question, Leanne.
Mm-hmm.
If you execute a query and then you send me the URL, can I retrieve the results of that query if given the URL?
You should do. I'm gonna let's try it now if you want. Do you want me to send you by Slack? You could.
Sure, I'll give it a try.
All right. There's the URL. I've just sent you by Slack the URL for the query I just executed. You could just open this notebook and then cut and paste it in, or just cut and paste these couple of cells here. I'll let Jeff do that in the background and he can tell us if he gets it. But yes, I expect that you will. The URL is not, URLs for jobs are not assigned to the people who executed them. Well, they shouldn't be. If we do find that Jeff can't access the results from this, I think we would have to pass that back to our science platform team to look at. While Jeff's doing that, do we have any other questions? No? Okay, and finally, cleaning up is always good. We all hate doing it, but it's a good thing to do. Once your job is finished and you've retrieved your results, you can delete your job from the server by hitting job.delete. Since Jeff is trying to retrieve some results from my jobs, I won't do that right now, but it will just delete the job. And then if you go back and try to retrieve the results, you won't get them. Once Jeff's come back and given us the result of his exploration, we can run that cell. If you don't run job.delete, don't worry. There is cleanup that runs automatically on the server and it will eventually clean up the results. How it does that is based upon various different considerations, mostly around the amount of storage available and you know, preserving results for, say, a minimum amount of time. Okay, and we are now exactly at 10 a.m., 1 hour, and that's the end of this tutorial. I'm sorry we didn't get a chance to go through the visualization aspects, but that also wasn't really the focus of what I wanted to talk about today.